In this video, we want to finish off our implementation of our mutable doubly linked list. So in the previous video, we started converting our singly linked list to a doubly linked list, and we got most of the methods implemented except for the hardest ones. We have remove, we have iterator, and we have insert all. It turns out the iterator is really easy to change. The only thing in here that needs to change is the reference to head. Well, we've done that a few times. Head changes to end.next. Oh wait, there is one other thing though. Rover never goes to null. When do we know that we need to stop? We need to stop because the rover walks back around to the sentinel. Remember, this list has no nulls in it. So that doesn't tell us to stop the way that it did for the singly linked list. We have a different condition, which is that we've hit the sentinel. Okay, what about remove? Remove, we have the same requirement on the nodes that we have. We decrement the number of elements so that we don't forget it. Previously, we had this condition again, though, because we had a special case if we were dealing with removing the first element. And one of the promises of adding a sentinel in a doubly linked list is special cases go away. So I'm just going to delete that if there. And let's see what we have to change. Well, the rover starts off at head, which in this case is end.next. We're going to walk forward. Now, our previous remove walked one shy of the element we wanted to remove. I actually want to walk all the way up to it. So I'm going to go from 0 until n, or I could have gone from 1 to n. Doesn't matter, whichever you feel more comfortable with. And then that means that rover is now on the thing that I want to remove. So the value that I'm going to return is rover's data. I don't have this if again because I don't have special cases, but I do need to set two pointers. The things I want to point things around rover. So to do that, I set rovers.prev.next to rover's next, and rover's next prev to rover's prev. And then we return this value. And that's remove. Now you can see the remove actually got quite a bit shorter because we got rid of the special cases. And because I don't have to worry about setting head and tail, I'm always setting a previous and a next, no matter what element I'm removing. And that's how it's going to work. Our last element is insert all. Okay, what do we need to do here? So we have our require. If they didn't give us anything to add, well, we don't want to do any work. Otherwise, we need to go through and add some new elements. Last time, for the singly linked list, I built up kind of a small list that was all the new elements that we were adding. And part of the reason for doing that is because in the singly linked list, the way it works, it can be challenging to insert things as you go, but in this case, I don't have to. Plus, I didn't want to duplicate code. So this code for creating the new list off the elements, I didn't want to have to duplicate that. And I had this if down here where I had to insert either at the beginning using one set of logic or later on using another set of logic. Well, once again, as we've seen other places, that if goes away because the sentinels kind of remove us from the burden of having that type of logic. So we're going to start our rover, and what I'm going to do is this logic is actually going to kind of, and it's not going to go away completely because I do need to walk through the elements and add stuff, but it's actually going to come later in here. So I'm going to paste it down there and then we'll wind up fixing it. So rover starts at the head, end.next, and I am going to walk from 0 until n. So I'm walking to the element at index n, okay, which means that the things I'm inserting are actually supposed to go before rover when we're done with that. And that's significant. That's what I couldn't do easily with the singly linked list. With the singly linked list, it's really, you can't insert before something. You have to go to the thing before where you want to insert and insert after it. With the doubly linked list, I have no problem inserting before. So I'm going to actually walk to the node that's currently at the index that I want. And then, while here, I'm just going to run through all of the elements, not just the tail of them. I'm going to run through all the elements. And for each one, I'm going to make a new node. But here, this will be val new node, is a new node with that data. And then how should it link in? Well, its previous should be Rover's previous. And its next should be Rover. Okay, so I'm literally making it so it's the thing right before Rover in the list. And then I have to link it in the other way. So I've basically made it point out. Now I need to make two things point it. So Rover's previous next is new node, and Rover's previous is new node. That adds a new element in, and I add it to my count. And then I get the next one, and the next one, and the next one. And I'm constantly doing this. I'm adding all of them before Rover, which is where they belong in the list. And now this code is happy. Okay, it compiles, and it doesn't have any errors in it. We haven't exactly tested it, but I'll just tell you I feel reasonably confident about this. I don't think and there's a possibility I have a minor typo, and it should be tested. But the thing to notice here is our previous code, our singly linked list. This is 106 lines of code. Our doubly linked list is 85. So even though the picture for the doubly linked list has a lot more arrows in it, okay, the singly linked list looks like it's a simpler thing. Because I had both a head and a tail, because I had the ability to append, the head and the tail led to a whole bunch of special case code that all goes away when we put our sentinel in here. And therefore, the code for the doubly linked list, even though it has to do things like set two pointers here, it's still simpler code because it doesn't have ifs with these big branches for one type of logic if you're doing stuff at the beginning, or a different type of logic if you're doing stuff at the end. It just has one set of logic, and that logic works for anywhere in the list. And that's why I like doing my linked lists using doubly linked lists with sentinels. So we've now seen how that gets implemented. We'll come back and we'll look at kind of yet another type of implementation of linked list, and this is actually the type of implementation of linked list that we've used the most so far in Scala.